Finally, we have enough information and knowledge to understand where little g, 9.8 meters per second squared, comes from. We've been using it the entire semester, and the whole time I've just told you to believe that it represents the free fall acceleration of an object on the Earth's surface, and that you can calculate the gravitational force with it if you multiply it by m. Now we'll see where it comes from. So consider an object that's freely falling. We'll draw a free body diagram for it. As you know, free fall means that there's only one force. There's only the gravity force. I'm going to label it Fg now, and not W, because Fg is our more sophisticated way of writing the gravity force. So Newton's second law says that the sum of the forces in the y direction equals this object's mass times its acceleration. We've got one force. This is the gravity force. It's directed downward, so it gets a minus sign. And it has a magnitude equal to capital G times the mass of this object, which I'm labeling with little m, times the mass of the other object that's causing the gravity force, namely planet Earth. So I'm going to label planet Earth's mass with a capital M and a subscript E. Now there's a distance here. Distance squared. That's the distance between the object and the center of the Earth, which, if you're near the Earth's surface, equals the radius of the Earth, more or less, plus or minus a few meters. Let me just draw a quick sketch to show you what I mean by this distance. Here's planet Earth. Here's a little ball that we're dropping. The ball falls. And we're saying that the distance between the ball and the center of the Earth is essentially equal to the Earth's radius. Depending on how high above the Earth's surface is, it might be a little bit more than the Earth's radius, but the Earth's radius is 6,371,000 meters. So if we're off by a few meters here, that it doesn't really make much difference. So that's what I mean by the distance here. Okay, let's do a quick step of algebra and cancel out those little m's, and we see that A equals minus big G times mass of Earth divided by radius of Earth squared, and I'm going to call this quantity G. So we know that AY equals minus G. We've been doing that all semester. And now I claim that this little g actually is the number you get when you do this calculation. So let's do it. And I encourage you to get out your calculator or whatever and do this computation with me, because it's cool to see it all come together. We're saying G equals 6.673 times 10 to the minus 11 newtons meters squared per kilogram squared times the mass of the Earth, which you can look up. It's It's 5.972 times 10 to the 24 kilograms. And then we divide by the radius of the Earth. The average radius of the Earth is 6.371 times 10 to the 6 meters. We square that when we put that on the bottom. And guess what? If you plug all that in, you get this magic number, 9.8 meters per second squared. That's where little g comes from. It is, put this in a box here. It's the universal gravitation constant times mass divided by distance squared. So this means that we can actually calculate a g, or free fall acceleration, for all sorts of other objects and situations beyond just being at the surface of planet Earth. For starters, you could figure out what g is, how fast an object would accelerate, if you were on top of a very tall mountain. Because if you were on a tall mountain, maybe there's a mountain peak on Earth, and there's your ball. Now this distance might be somewhat significantly larger, a few thousand meters larger. So it could actually make a fairly significant difference in this number, and you'll find that the free fall acceleration on the top of a mountain is smaller, maybe like 9.7 meters per second squared. So g is not actually fixed, it depends on how far you are from the center of the Earth. Now the next thing that you could use it for is to look at other astronomical bodies. This works if you're on the moon. You put in the moon's mass, you put in the radius of the moon, and now you find that the gravitational acceleration on the moon's surface is about 1/6 as much as it is on the Earth's surface. And in the next example, we're going to do an analysis of the acceleration if you're on an asteroid.